if the diagonals of a cyclic quadrilateral are diameters of the circle through the vertices of the quadrilateral, prove that it is a rectangle. Here first we have a cyclic quadrilateral. What do you mean by cyclic quadrilateral? Where the four vertices are on the circle, so which is A, B, C and D. These are the four vertices. So A, B, C, D is a cyclic quadrilateral. So let's write that. Then there's another feature of this cyclic quadrilateral. The diameters of the circle pass through the vertices of the quadrilateral. So we have the diameters. One BD is the diameter. Here is the center, and here is the other diameter. The diameter are the other diagonals. So we write that too. So we have AB, AC and BD are diagonals that pass through the center. And we need to prove that ABCD is a rectangle. So we start the proof. The first thing is, here we have the diameter. If this is the diameter, we can say angle A is 90. So BD is diameter. Therefore angle A, or we call it DAB, equal to 90. And on the other side here also, this angle also will be 90, because these are angles in the semicircle. Here you have this angle is in the semicircle, it will be 90, and this angle is also in the semicircle, and that will be 90. BCD equal to 90, and the reason angles in a semicircle are 90. Now we'll take up the other diagonal, and we'll take up the diagonal AC. Now if AC is a diagonal, angle B, this is the angle in the semicircle, this will be 90, and on the other side this angle will also be 90, because it will be angles in the semicircle. So AC is a diameter. So we have angle ABC equal to 90 and angle ADC equal to 90. This is angles in a semicircle. Therefore now if you look up in the quadrilateral, all the angles are 90. This we proved first was 90. Now we show this also is 90. So in a quadrilateral where the angles are 90, it is a rectangle. So in quadrilateral ABCD, angle A equal to 90, angle B equal to 90, angle C equal to 90, angle D also equal to 90. Therefore ABCD is a rectangle. So here is A, B, C, D. It is cyclic quadrilateral. Now the diagonals pass to the center. So here we have the center. We have this diagonal BD passing to the center, and because this is a diagonal, we know this angle is 90. Angles in a semicircle, and this also will be 90, because this is an angle in a semicircle, 90, and this angle is also in the semicircle, so this also will be 90. So we have angle A equal to 90 and angle C also equal to 90. Now we'll take up the other diagonal. The other diagonal is AC. Now when we take up AC, so we'll have now B will be 90 because AC is the diameter, and we have this angle D also will be 90 because D is in the semicircle. So for AC is diameter, so angle B equal to 90, and angle C and angle D is also 90. Earlier we took up here and we said this was 90 and this also was 90, so all the angles are 90. It is a rectangle. This is 90, this is 90, 90, 90. It becomes ABCD is rectangle. If the non-parallel sides of a trapezium are equal, prove that it is cyclic. So here we have a trapezium with its non-parallel sides equal. So ABCD is a trapezium, which means these are the parallel sides. So we say given ABCD is trapezium where parallel sides are AB parallel to DC. Now the non-parallel sides are AD and BC, and they say AD and BC are equal. AD is equal to BC, so let's write that. So AD equal to BC. We have to prove it is cyclic. Prove ABCD is cyclic. Now how do we prove it is cyclic? All we need to show is this angle D plus B is 180. So we just have to show that angle D plus angle B equal to 180. Now to prove this we have to do a construction. We'll construct this point. We'll call this point P such that CP is parallel to AD. So for construction we construct CP parallel to AD. Now here to start we have a parallelogram. We have DC parallel to AP here, and now we have AD also parallel to CP. So in the first step we'll take quadrilateral APCD and we'll say CD parallel to AP and AD parallel to CP. This was given and this is constructed. Construction. So quadrilateral APCD is a parallelogram. Now if it is a parallelogram, we'll mark this angle as 1, 2 and 3. We can say angle 1 equal to angle 2. We write this as equation 1. This is opposite angles of parallelogram. And also we can write AD equal to PC. Here AD equal to PC. And the reason is again opposite sides of parallelogram. But in the beginning it is also given to us that AD equal to BC. So we have AD is also equal to BC was given to us in the beginning. So this is equal. So we write that AD equal to BC is given. So when we compare we can say PC equal to BC. If PC is equal to BC, so here we have PC equal to BC, so these two angles will be equal. Angle 3 will be equal to angle 4. These are angles opposite equal sides. We have a linear pair. This is 2 and 3 is a linear pair. So I'll write angle 2 plus angle 3 is 180. But we know angle 2 is equal to angle 1. And we know that angle 3 here is equal to angle 4. So angle 1 plus 4 is also 180, which means B plus D equal to 180. 1 is, have you seen this? This is 1 is D and this is 4, 180. So these opposite angles are supplementary. So it is a cyclic parallelogram. It is cyclic, not a parallelogram, it is just cyclic. So here I can say A, B, C, D is cyclic, because we have shown here this plus this is 180. So this was given to us a trapezium where they said non-parallel sides were equal. So we drew a line parallel here, we call it P. So we had this also parallel, then we had now we got a parallelogram, the first step. This was our parallelogram, and because it is a parallelogram, I could say these two opposite angles plus this angle is equal. So we have angle 1 and angle 2 equal. That was one step. Then the next step was, we know AD is equal to PC, opposite sides of parallelogram. But we also know AD is also equal to BC, was given to us in the beginning. So AD equal to BC was given in the beginning, and we know AD equal to PC. So we have these two sides equal, which means the base angles will be equal. These two base angles will be equal. And we'll call these base angles as 3 and 4. Then we have a linear pair. So we'll just write here angle 3 equal to angle 4. The next step was a linear pair. This was a linear pair. So we had 2 plus 3, 180. But we know 2 is equal to 1. So 1 here. And we know 3 equal to 4. So 4 also equal to 180. So we got, now we have the opposite angles, that is D plus 4. There's 1 plus 4 is 180. So B plus D equal to 180. So I can say A, B, C, D is cyclic. Two circles intersect at points B and C. Through B, two line segments A, B, D and P, B, Q are drawn to intersect the circle at A, D and P and Q respectively. Prove that ACP equal to AQT. So first let's take up this first circle. Here we can draw two angles in the same arc, and that's this angle here, and from the same point here we have this angle. We have taken the points arc P and A. We've seen we have this angle here will be equal to, from the same point P and from A you go here, these two angles are equal, angles in the same arc. We'll mark them as angle 1 and angle 2. So we call PBA as angle 1 and we have angle PCA as angle 2. Let me just repeat this. This is PBA, which is angle 1, and then we have PCA, which is angle 2. And we can say angle 1 equal to angle 2, angles in the same arc. Now we take up the next circle. We'll take up this circle, and if we take up the arc DQ, from arc DQ we can draw two angles. Here we go up from DQ, we get this angle. Then again from DQ we go up, from Q we go up and we get this angle. These angles again will be equal. We'll mark them as 3 and 4 because they're angles in the same arc. So first we had angle DBQ. Now angle DBQ is this, DBQ. It is angle 3. And then angle 4 is DCQ, is angle 4. Let's just mark that. DCQ. This is angle 4. And angle 3 equal to angle 4. Angles in the same arc. So we mark this as equation 1. And here equation 2. Now if you see, angle 1 and angle 2 are vertically opposite angles, so they will also be equal. So angle 1 equal to angle 3, vertically opposite angles. But we know angle 1 is equal to angle 2. Angle 1 was equal to angle 2. We proved this. So angle 2 will be equal to, and we know angle 3 was equal to angle 4. Equal to 4. If 1 equal to 2, 1 equal to 3, 2 equal to 4. This is by statement 1 and 2. And 2 angle is 8ACP equal to angle QCD, and this is proved. Let's go over this again. So in the first step we had these two, we had this angle here equal to this angle here. So we had angle 1 equal to angle 2, angles in the same arc, 1 equal to angle 2. Then on the other side we had this here, this angle equal to, here again angles in the same arc. The arcs were DQ. So we wrote this as 3 and 4. So this is P and A. So we had again angle 3 equal to angle 4. Now angle 1 is equal to angle 3 because vertically opposite angles. So angle 1 equal to angle 3, vertically opposite angles. But 1 is equal to angle 2 here, and 3 is equal to angle 4. So 2 also will be equal to 3. So since 1 is equal to 2 and 3 is equal to 4, now we can say angle 2 is equal to angle 4. Proved. If circles are drawn taking two sides of the triangle as diameters, prove that the point of intersection of the circles lie on the third side. So first we have a triangle which is APQ. Now taking AP as the diameter, you draw a circle. And next, taking AQ as the diameter, you draw another circle. Now we need to prove that the point of intersection of these circles, which is B, lies on PQ. It lies on the third side. This third side of the triangle. This is the third side. AP is one side, AQ is the other side. We have to show it lies on the third side. So we'll say given triangle APQ, then we have AP is diameter of C1, of circle 1. So I'll just mark that here. AP is the diameter of circle 1. This is circle 1. And on the other side we have AQ is diameter of circle 2. So AQ is diameter of circle 2. What we need to prove is the point of intersection. We need to prove the point of intersection is here B. We need to prove B lies on the third side. So prove B lies on third side. The third side is PQ. So first let's take up the first circle. We'll take up C1. In C1 we'll take the proof. In C1 PA is diameter. If PA is diameter, I can say this angle is 90. Angle 1 will be 90 because the angle in a semicircle is 90. So you have got angle 1 equal to 90. Reason, angle in semicircle. Just put it in red. So I have this angle is 90. Similarly for the other circle in C2, this is circle C2. So we have AQ is diameter, and if AQ is diameter, then I can say this angle here will be 90. Angle in a semicircle. Angle 2 will be 90. It is angle in the semicircle. So angle 2 is 90, angle in semicircle. So here now we can see that angle 1 plus 2, angle 1 plus angle 2 is 90 plus 90 equal to 180. Therefore PBQ is a straight line. If it is a straight line, we can say B lies on PQ. Straight line means 180. 180 means it's a straight angle, straight line. Let's go over it again. So if AP was a diameter, we have AP is a diameter, so you will have this angle is 90 because angle in the semicircle. This is a semicircle. And on the other side, if AQ is diameter, that means this angle will be 90. This is again angle in a semicircle. So these two angles are now 90 and 90. This angle 1 is 90, angle 2 is 90. So this becomes now 180. 90 plus 90 equal to 180. So PBQ is a straight line. ABC and ADC are two right triangles with common hypotenuse AC. So I have AC, and from AC I have two right angle triangles. So one is ABC and the other one is ADC. The right angle triangle. So this angle is 90 and this angle too is 90. So in the first step we'll say AC, here we have AC, and then this angle is 90, which means A, C, D all lie in the same circle. So we'll write here angle ABC is 90. Therefore ABC are concyclic. They lie in one circle. Similarly, we can say for AC, and this is 90, so this also lie in the same circle. Angle ADC is 90, therefore ADC are concyclic. So both these have the same common diameter AC. So I could say all All these points lie on the same circle. A, B, D, C lie on the same circle. So A, B, D, C lie on same circle. So let me draw the circle now. So this will be the circle. That now I need to prove that angle CAD equal to CBD. Now where is CAD? This is CAD. CAD. This angle equal to CBD. CBD. And these are equal because they are angles in the same arc. So angle CAD will be equal to angle CBD, angles in the same arc. So they will be equal, and we have proved that these two angles are equal because they're angles in the same arc. Here we have this arc here. Let's mark it here. This arc, and here this arc, and this angle. They all belong to the same arc CD. We'll go over it again. So first we had a right angle triangle ACB, where this is 90. So we can say ABC was concyclic. They all lie in the same circle. So you have ABC concyclic. Then we had another right angle triangle, and that right angle triangle was ACD, and here too this was 90. So I could say now that ADC is concyclic. Now ABC is concyclic, and for ABC the diameter we saw was AC, and for ADC also the diameter is AC. So with putting both these together, I can say all the 4 points A, B, D, C are all concyclic. They all lie in one circle. So here I have one circle. A, B, C, D lie on a circle. Now that I have a circle, I can show that the angles are equal. So if I take this angle CAD, here is CAD. CAD belongs to the arc CD. So this is CAD. And the CAD will also be equal to CBD. It will be equal to this, angles in the same arc. So I'll have angle CAD equal to angle CBD, angles in the same arc. Prove that a cyclic parallelogram is a rectangle. So given say ABCD is a cyclic parallelogram, we need to prove it is a rectangle. ABCD is rectangle. Now let's take the properties. Number one, they said that ABCD is cyclic. So if ABCD is cyclic, I'll just draw it up here. I can say A plus C equal to 180. A plus C equal to 180. Say it is X and X. Not X and X, I don't know, they're equal. A plus C is 180 because opposite angles of cyclic are supplementary. Now on the other side they say it is a parallelogram. So ABCD is parallelogram. So let's put the properties of parallelogram. So here ABCD is also a parallelogram. So what are the properties of parallelogram? We know A is equal to C. A equal to C because opposite angles are equal in a parallelogram. So earlier it was given to us, now we had said A plus C equal to 180. Now A equal to C, that means I can write A plus A equal to 180 because A is equal to C. It is a parallelogram. So 2A equal to 180, A will be 90. Now if A is 90, C also will be 90, opposite angles are equal. B also will be 90 because it's supplementary, and D also will be 90. So here I have now all A equal to 90, B 90, C 90, and D also 90. So ABCD is a rectangle. So I have ABCD is a rectangle. We go over again. So first property was saying it is cyclic, and because it was cyclic, the property was A and C, A plus C 180. And then it was a parallelogram. It was a cyclic parallelogram. So AC were equal, X and X. X and X, because it is a parallelogram. Property of parallelogram, A equal to C. So we put this value here. So I'll put for A, and for C also I'll put A, because A we know is equal to C, 180. So 2A 180, A equal to 90. So here in this parallelogram, all the angles will become 90. If A is 90, your C also will be 90 because they're equal. And we know A plus B is, in a parallelogram, A plus B is 180. So this also becomes 90, and your D also becomes 90. Since all these angles are 90, it is a rectangle. See, we know A plus B is also equal to 180. We said A was 90, B 180, so B also is 90. If B is 90, C also is 90, D also is 90, because B and D are opposite.